Hello everyone, my name is Nikhil Agrawal from ISC Bangalore. My research work is in the field of Android app security side with a special focus on analyzing Indian financial apps. As we all know, financial apps are used a lot on a daily basis, like for paying bills, funds transfer, checking bank balance, etc. But at the same time, it has been observed that there are attacks that is happening on the financial apps. Like there was a report which says that 70% of the top 100 mobile banking apps are vulnerable to the security attacks. Hence, it's very important that the financial app developers are following best practices to make their apps highly secure. To help this, there is a non-profit foundation named OVAS, which helps in improving the security of software. In 2018, they released a document named Mobile Application Security Verification Standard. It establishes the baseline security requirements for the mobile apps. They recommend the app developers to put various self-defense checks in the app, like anti-tampering, root detection, emulator detection, and so on. They also recommend that the trivial static analysis of the APK should never reveal any important code or data. However, adoption of such methods is completely left to the developers, and it's not mandated to have such checks in the apps. Also, code tampering is identified as one of the top 10 threats to the mobile apps. Motivated by this, we study the extent to which the financial app developers follow OWASP guidelines to make their apps highly secure. That is, we first find whether the financial app developers are putting these self-defense checks in their apps, and if such checks are present, can these checks be bypassed if we try to locate the related code from keyword-based search using various reverse engineering tools? Now, I'll be discussing few backgrounds related to this work. Every Android app that we use behind the scene, it is actually an APK file, which is an archive file. So when you try to extract its contents, this is how it looks. It contains various informations, and every file has its own usage. Every Android app installed on the mobile device is uniquely identified by its package name. Android mandate that every APK has to be digitally signed. Also, this index files, shared object files, which are present in the APK, these files can be decompiled to understand the code semantics. Example, uh, there's a reverse engineering tool named JEDEX, which actually converts the DEX code to the Java code to get a high-level idea regarding the code semantics. Similarly, there are tools like Radare2, Ghidra, which can actually decompile the C++ code. Now I'll be discussing about the various self-defense checks that this work has focused on. First is anti-tampering. Anti-tampering checks are there to protect the app against repackaging attacks. Repackaging of a mobile app means taking the original app, inserting some malicious logic into that app, and then rebuilding this tampered app and uploading this app to the alternative marketplaces. During this procedure, the public key certificate, which is used to sign the APK, that gets changed with respect to the developer's public key certificate. Hence, performing the certificate validation can be a useful idea to protect the app against repackaging. Android does provide few APIs to perform these checks. Next check that we are focused on is the root detection. These checks are there to make sure that the app is not running on a compromised device. And these checks can be performed by checking the presence of a super user binary or any malicious app which is installed on the device. Third check that we are focused on is the emulator detection. These checks are there to make sure that the app is running only on the physical device, and these checks are related to finding the build related information about the app's device. The last check that we are focused on is the dynamic instrumentation framework detection. These frameworks have the capability to alter the flow of execution of app without statically modifying the APK. Few frameworks include like Frida, Expose frameworks, and many others. I would like to discuss the threat model. We believe that the user has given the permission to install the app from unknown sources, as by default, Android doesn't allow the users to install the app from sources other than Google Play. We believe that this assumption is reasonable because there was a report which says that 30% of the app installation in India is happening from a file transfer app like Share. Coming to the threat model from the attacker's side, we believe that the attacker doesn't have the access to the source code of the app as well as to the developer's private key. However, he has an expertise in the various reverse engineering tools like APK tool, Gitra, Radar2, JetX, and so on. Attacker can always upload the tampered version of the original app and upload it to the alternative marketplaces. An attacker can also compromise the end user's device by routing. Let's assume that the self-defense checks are present in the app. Now we are curious whether this check can be bypassed if we try to locate the code from keyword-based search. So for this, we have actually used a reverse engineering tool named APK tool, and we have done the Smally code instrumentation. This Smally code is a human readable format for the Dalvik bytecode. For each of the self-defense checks, we prepared a list of Android APIs, which is used to perform the validations. So this is a high level of flowchart. We take the APK, we disassemble it using APK tool, and we find the relevant Smally files in which the corresponding code is present using the grep command. Then we did the code injection over there. We rebuilt the APK, we signed it using APK signer, and then we launched this modified app to identify whether this app is working in the same way as if the original app would have run. So among the 4 self-defense checks that we have focused, in this talk, I'll be focusing more on the anti-tampering check and how we have bypassed it. So for the anti-tampering check, certificate validation is performed. So first, we fetch the developer's public key certificate, which is used to sign the APK. So on the screen, you can see this is a scenario of a public key certificate provided by the HDFC Bank, and this certificate is used to sign one of their apps APK. So once the certificate is fetched, we located the code snippets where this public key certificate details is used to fetch. So this is the Java code snippet, which is used to perform the certificate validation. And for this Java code, this is the equivalent Smelly code. And in this Smelly code, we have done the instrumentation and we have injected the developer's public key certificate details, which I shown earlier. Now for this Smelly code, this is the equivalent Java code, how it looks for the illustration purpose. Now we rebuild this modified APK, we resigned it, and then we actually analyzed whether we have successfully bypassed this check on. So now I'll be showing a very small demo regarding how we have bypassed the anti-tampering check. So this is the HDFC. So let's launch the HDFC original bank app. So this is how it looks. It's launching, and then it will ask for the customer ID and password. So this is how an original app is working. But when we resign this APK using my public private key, let's say, so this is how it looks. It will show an error message now. It's saying something went wrong while executing the current transaction. Please try again. So it means that the app does have the anti-tampering protection present in the app. Okay. When we launch the broken version, like the tampered version of the app by doing the relevant code injection, this is how it looks. This is the same as it's the same behaving as if the original app would have run. You can also see a toast message presenting this is a broken app. And here also it's asking for the customer ID and password. So this app is behaving as if the original app would have run. So in this manner, we have successfully bypassed the anti-tampering protection in the app. Now I would like to conclude my talk by giving few recommendations to the app developers. First, the SDC related code should never be locatable from trivial static analysis, that is from keyword based search, because if such checks are present, it can be easily bypassed. And these checks are good for nothing. We recommend the app developers to write the SDC related code in C++, because once the C++ are compiled in the APK, this is mapped to a shared object file, and decompiling the shared object file is challenging than analyzing the Java code, which is present as a text file. We also recommend the app developers to use the Google SafetyNet API to perform such checks so that to make the life of the attackers really hard to bypass these checks. Thank you.